Yeah, sure. Please go ahead, Yuri.
All right, thanks. Thanks everyone for coming. So I will continue my last week's talk about generalized pure solitons. And specifically, I will move into complete setting. But before I really move, let me clarify one point, which I believe I didn't make clear last time. So maybe let me fix two separate definitions for solitons. So we'll say that manifold and family of metrics and family of three forms is steady, generalized, Ricci soliton if there exists a time-dependent vector field xt, so it's time-dependent vector field, such that the generalized Ricci flow, which I recall defined as a flow of metrics defined by the following system of equations, so that this system of equations, so the G and H solves the system, and the relation with respect to vector field, that actually these evolution terms are given by the flow of diffeomorphisms, local flow of diffeomorphisms defined by the vector, by the time-dependent vector. So this thing equals xt of G, and this thing equals Li of H. So this is what really is the fixed point modular diffeomorphisms. And such objects are difficult to study and find and really describe because of this unknown vector field, which we don't really have a good control of. And this was the state of the art before Perelman's work for the Ricci flow as well. So this was like the best way we could define and think of steady Ricci solitons. Somehow, if your manifold is compact, so if M is compact, generalized Ricci soliton, then there necessarily exists a smooth function f such that xt equals, well, to match the usual notation, I guess I want to make it minus grad f. So in particular, Ricci minus 1/4 H plus hash and f equals 0, and maybe not even in particular, maybe I should add right and. So this is really the system of equation which happens to be satisfied in this case, and such structures will be called gradient steady generalized Ricci solitons. So, but in particular, theorem tells you that any steady generalized Ricci soliton must be gradient steady generalized Ricci soliton. And the proof uses this Perelman's lambda functional, which I recall is defined as infimum of f functional. Maybe I'll just write it. So infimum over normalized f. And the observation that if you have, so first this lambda is achieved for a smooth function. So second, that it is non-decreasing. It is constant if and only if GHF is a gradient generalized Ricci soliton. Is a gradient steady generalized Ricci soliton. So here this function is unique in the first part. So obviously I'm using here some structure results about this function, about its minimizers. So the key point here is that if you have a steady generalized Ricci soliton, then this function of being invariant under the diffeomorphism group will be constant on such a soliton, and constants imply that it must be a gradient soliton. So that's really the reason why on compact manifolds we study gradient solitons, and on incomplete setting, which we'll be discussing today, we will be also interested in gradient solitons, because we're really interested in the objects which appear as limits of flows on compact backgrounds, and such limits might be complete as well. And they are expected to be also gradient steady Ricci solitons, even though we do not have a complete argument for that. So in all the cases where we know existence of such solitons, they are gradient, but on a general complete background, we do not have an argument for why such soliton must be complete.
I have a question. So this argument that solitons has to be gradient on a compact manifold, are there some direct arguments for that? Just like Bianchi identities?
No, not to the best of my knowledge. I don't know such argument.
Yeah, no, I don't think so.
So the only available argument is through this
functional F.
functional. Thank you.
And also, it's probably worth mentioning that, like in the complete setting, like if you have bounded curvature, for instance, you can make this same theorem work, I guess.
Yes, exactly. Yeah, right. If
as long as the F functional is well defined, you basically can.
Yes, as long as you can make sense of this integral, and you can integrate by parts, and you can set up appropriate functional space for smooth function f's, which maybe go sufficiently fast to a constant at the ends of your manifold, then you can make this. You can define the same quantity, and you can run the same argument. And there are even like arguments for some intermediate decays at infinity, which uses this mass from general relativity, but yeah, it's probably. I mean, I know that such things exist for Ricci flow. I'm not sure if they have exact formulation for the generalized Ricci sense. So the question which we're going to discuss is what are complete generalized Ricci solitons, and specifically we'll be working in generalized scalar setting. Maybe let me specify the above definition. So if you have a generalized scalar manifold MGIJ, we will say that this is a gradient steady generalized scalar soliton if M, G, and H, which is given by DCI omega I, is a gradient steady generalized Ricci soliton. So basically, being a soliton or not is completely determined by metric G and the corresponding torsion for free form H. And you can swap I with J here. The effect it will have that H will be substituted with negative H, and the equation, the soliton equation, will still be satisfied. Okay. So the result, which I mentioned last time. So this follows from prior works of Jeff and our work, our joint work on Hopf surfaces, that if you have a surface which is gradient steady generalized scalar soliton, Ricci soliton, and M is compact, then either MGI and MGJ is Calabi-Yau, or MI is biholomorphic to the Hopf surface. This parameter alpha beta. This is Hopf. Okay, strictly speaking, I need to take universal cover, not some appropriate cover of it. And the appropriate cover of it with respect to J will be as a complex manifold isomorphic to M alpha beta bar. And under some extra assumptions, we have really uniqueness here as well. So we can exactly tell that the metric part should be isometric to the soliton which I described last time. But not in general. In general, we do not know that yet. So today we're going. Yes.
Sorry. Is there any subtlety to define a steady generalized scalar solitons when the vector field is not gradient, or is just the same?
When vector field is not gradient, well, I mean, again, compact, they are always gradient, and non-gradient, I imagine they must exist because they exist for the Ricci soliton to start with.
But it's the same. It's the same definition. It's just that MGH.
I mean, yeah, this is the first definition which I give. Okay, yeah, okay, I see your question. Yeah, you can use this and define non-gradient solitons, of course. Yes, you can use this definition with some arbitrary one-parameter family of vector fields. Okay, but we will be focusing today on the gradient solitons.
So in this theorem, it's up to biholomorphic transformation or up to?
So yeah, here is biholomorphic.
And you have examples, but you don't know whether every possible soliton is one of those.
Yes, exactly. Because we don't essentially do not have uniqueness in this part, which we discussed last time. And yeah, maybe with like developing further this work with which like Jeff and Mario, and so they're doing on this on the run hope they managed to prove uniqueness. So the hope is that maybe somehow this could be also used to settle uniqueness on non-round hopes, with where norm of alpha, non-standard hopes, where norm of alpha is different from the norm of beta. Okay, so so the question which we're going to discuss today, what about complete solitons? So yeah, let me specify that here I'm talking about four-dimensional manifold space, of course, in this theorem above. So you can define solitons in any dimension, but this theorem and what I'm going to discuss today will be about four dimensions. So we will add several assumptions. So first assumption which we will add that I and J induce the same orientation. Otherwise, if they use opposite orientation, you will have this local holomorphic foliation in two directions from the results of Vesti and Marco. And again, from the complex geometric point of view, at least, this is very special. We wanted to construct some new example, maybe with some new behavior. So second thing, which we assume here, assuming that they have the same orientation, so you have this commutator, and we say that it will be generically invertible. So you'll have this operator which is generically invertible. Again, in 4 dimensions, this is not really an extra assumption. This happens automatically as long as I is not plus or minus J globally. So which assumption do I also want to make? So one more assumption, which at this point looks natural and kind of innocent, but this actually will have there will be a serious ramification here, and there will be a second part of the entire conjectural classification, which is unfinished because of this assumption. So we assume that the Riemannian manifold has the smallest possible isometry group. Okay, maybe actually, yeah, go ahead.
Are you going to comment on the proof of the previous theorem?
Or? Well, I wasn't planning to. So, but basically, it is known which surfaces, in principle, could possess generalized scalar structure, and from what was known before, the really extra input which was required to make it is to make us to construct solitons on Hopf surfaces.
Thanks.
So you need to exclude topologically because of some churn.
Yeah, basically yes. So most of the surfaces are excluded from the consideration of the canonical divisor.
Yeah.
This canonical divisor will be disconnected. You'll have two loci where I equals j and I equals negative j if you're in j if you have an even type structure, and if you have odd type structure, we have even uniqueness statement. So yeah, from now on, I would like to move on to this complete examples. Maybe let me also add zero assumption, which is kind of trivial. I assume that neither MGI and MGJ are not scalar. Again, this will be sort of trivial to consider. So if these two are not scalar, then the smallest possible isometry group under this zeros assumption will be one-dimensional. I will comment in a second on it. And under the assumption that it's actually one-dimensional and it doesn't have a larger dimension, we will be able to get a complete classification. Well, with extra technical assumption about the curvature, but I will get to it when I will state the result. So let me comment about this isometry group. Remark. if MGIJ is a generalized scalar, it's a four manifold such that IJ, actually what I need, okay, it's generically invertible. Then I will necessarily have that Lie form of one complex structure equals negative Lie form of the other complex structure. And if it solves steady gradient generalized Kähler Ricci-Soliton equation, the system which I discussed, then what you immediately obtain that you will have vector field VI which is I holomorphic. You'll have similarly vector field Vj, which is J holomorphic. And you will have K-link vector fields, IVI and JVJ K-link vector fields. And if your background is not Kähler-Ricci flat, then necessarily your isometry group will be at least one-dimensional, because at least one of these two vector fields will not vanish.
I have a question about this condition, actually.
Yeah.
If you, for instance, consider actually instead of minimal, maximal, so for instance, cohomogeneity 1 will also impose this condition.
Mm-hmm.
So do you really need minimal condition, or what you really mean that this the wedge of these K-link vector fields is 0?
Well, I need two things. Yeah, I can comment on it. So I first need that the wedge is 0. This is what we call rank 1. But for technical reasons, at many points we used the vector field, the action of the corresponding vector field. So it generates an R action, which might not be effective. So it's either R action or S1 action. So we need this action to be proper. And it's not necessarily the case on the Hopf solitons, which we have constructed this vector fields. The corresponding action is not proper, for instance.
But on diagonal Hopf, I suspect.
On diagonal, it is. On standard, it is. On diagonal, it's not not
Yes,
necessarily.
on standard is actually the isometry group is much higher, even.
Yeah.
By the way, in relativity, when physicists classified Einstein solutions with certain K-link tensors, actually such conditions imply more symmetries actually than the generic case. When you have
yeah, probably that's what happens in our case. Okay. We really thought that this will be a more general case, and when it will have larger symmetry, maybe it will be more special. But yeah, it turns out that it's sort of vice versa. So these happen to be more rigid, and maybe that's the reason why we were able to completely classify those. And when there is a larger symmetry group, they will be less rigid in some sense. Possibly, again, we don't know what happens when the symmetry group is larger. But yes, that's exactly what we observed. Yeah, that's true. Are there any questions? So now this assumption 3 about this isometry group being small as possible, specifically being one-dimensional, and with the presence of two K-link vector fields, you necessarily observe that they must be aligned with each other. So everywhere this bivector must be 0. And also must generate S1 or proper R action. because if it's not proper, you can take closure in the isometry group, which is a Lie group, and you will have a larger isometry group. So in this case where it's proper R action, it can be actually obviously reduced to S1 action just by quotienting by the Z group, which sits inside R. So this will be free action, and Z will be integers inside will also act freely. So the quotient will be a honest manifold, and it will be a manifold with S1 action. So really, this will be our standing assumption, and having proper R action could be reduced to it. So now this assumption that I and J is generically invertible, it allows you to cook up a bunch of useful tensors. First, it allows you to cook up a symplectic form. So the symplectic form, I will write it as J inverse G. So this will be symplectic form. But unfortunately, it will not be everywhere defined. It will be defined on the dense open set. Specifically, it will be defined on M minus something I will call T. So T is essentially the support of the canonical divisor. So T is a set of points where I equals plus or minus J. And using all the usual standard symmetry relations for generalized Kähler structures, this omega, it will be a common real part of two holomorphic 2-0 forms, one 2-0 form for I and another 2-0 form for J. So omega equals real part of omega I. Equals real part of omega J, where omega I belongs to 2-0 I, omega J belongs to 2-0 J, and they are both del bar closed. So del bar I omega I equals del bar J omega J equals 0. So, and this is actually quite a familiar picture. Okay, maybe before I move to it, let me actually discuss it with this condition, what this vector fields. So, how do I want to tell it? Let me formulate it as a proposition. I will not really prove it, but it just will explain what we need. So in general, if both IVI and GVJ are non-zero, and they are generically aligned, so it means that they are aligned everywhere because they are aligned on the dense part, and they both are respectively I holomorphic and J holomorphic, it means that there is a vector field which simultaneously I holomorphic, J holomorphic, and also preserves G. So up to switching I and J, one of the following holds. So IVI is non-zero and J holomorphic on top of being killing and I holomorphic. So they both are 0. And in this case, MGI J is just hyperkähler. Or there is this kind of a bit sporadic case that locally MGI is isomorphic, biholomorphic to the standard Hopf. So these two are actually obviously special cases, both of them. So really what we'll be interested in, we'll be interested in the case where this vector field is both I and J holomorphic and preserves G. And again, this will be really automatically satisfied as long as you assume that both IVI and GVJ are non-zero. But then actually can happen that one of them is zero, and then you will need to argue why this vector field also preserves the second complex structure. So from now on, there will be standing assumption that there exists a vector field X such that IVI is some constant times this vector field, and GVJ is some other constant times this vector field. I'll have to write this in this generic way because some of these real constants might be zero. And X preserves GIJ. So it is scaling and real holomorphic with respect to both I and J. And again, it naturally, existence of such vector field naturally follows from the standing assumptions on the generalized Ricci gradient generalized Ricci soliton. Okay, at this point, I would like to make a detour to something maybe more familiar and maybe more classical, and this is Gibbons-Hogging ansatz. And before I do this, I observe that the fact that X preserves this structure means that on the complement of this divisor, where I equals J and I equals negative J, specifically on the complement of the set where symplectic forms are not defined, X preserves three symplectic forms. These forms are omega, I omega, so we just hook I into one of the coordinates, and J omega. So they are symplectic forms because of this. So these are specifically imaginary part of omega I and imaginary part of omega J. And this setting, when you have a vector field preserving a triple of symplectic forms, this is something familiar, which appears in other contexts. And this is where I want to discuss a bit Gibbons-Hogging ansatz. So I'll spend some time discussing it because it will be sort of the main building block and the main idea behind the entire construction and classification. So let's assume at this point that we have four-dimensional, not even necessarily complete, for the sake of what I'm going to discuss, manifold. So this will be hyperkähler. It means that M manifold, metric, and either of these complex structures will give you a Kähler structure, and I, J, and K satisfy quaternionic relations. Or in other words, you have this triple of complex structures satisfying quaternionic relations, which are parallel with respect to Levi-Schmidt connection. So it means that the holonomy group, the remaining holonomy group, is a proper subgroup of SP1. Not proper, as a subgroup possibly not entire of SP1. So, and we assume that X is a vector field preserving the entire structure. So preserving G, I, J, and K, which actually can be expressed from the previous ones. And in particular, it also would preserve the three symplectic forms, the Kähler forms of the corresponding complex structures. These are symplectic forms. So this observation that you have as a vector field, maybe also let's assume that as before that it generates S1 action. It allows you to cook up, at least locally, a hyperkähler moment map. You will have three closed symplectic forms. Oh, sorry, closed one forms. Closed one forms. And if you assume on top of that, if they are exact, which is true either locally on M, or it's true on the appropriate cover of M. So in this case, you can write them as dmu1, dmu2, and dmu3, where ui are just smooth functions of your manifold. So and this gives you a map from your manifold to R3. So maybe which I assemble into one map mu. And this map mu is constant on orbits of S. Of S1 action on your manifold. So really it goes through the orbit space. But to do some differential geometry on this manifold and on this quotient, it really is helpful to first remove points with the locus on which the action is not free. And S1, the action of S1 on the hyperkähler manifold is free on the complement of the fixed points. Fixed points. Maybe I call this M0, where I take M and I remove all fixed points. And in this case, you will have the quotient. You will have a principal S1 bundle. So this is just projection of the quotient. This is principal S1 bundle. And the base space of this principal S1 bundle through the moment map will be mapped to R3. So this is how moment map descends. So this will be moment map. Moment map. It is well defined because the initial moment map was constant on orbits of S1 action. And this open map, this moment map is a local diffeomorphism. Or you can say it's just an open map. So this is something three-dimensional. This is also something three-dimensional. So it's an open map of three-dimensional manifolds. So if you look at this picture, you could cook up a co-frame in M0. So this picture gives you co-frame in the cotangent space of M0. Specifically, you have three one forms which are pullbacks of one forms from R3, and you have a connection one form. Connection one form of the principal S1 bundle. So this is like a coframe. And in principle, you should be able to write down all your structure in this coframe. It happens that in this coframe, the entire structure, the hypercalculus structure, which in principle is a complicated set of nonlinear partial differential equations. But situation simplifies drastically here exactly because of the presence of this extra one-dimensional symmetry.
Sorry, how did you choose the connection one form? I didn't got this part.
M is a Riemannian manifold, right?
Yeah.
So it has a metric, and you can take orthogonal projection onto the vertical directions. So strictly speaking, it will be connection form with the values in the Lie algebra of S1, but you can identify it with real numbers.
So what is the curvature of this connection?
Yeah, I will mention it in a second. Yeah, it's not obvious so far from what I have described. So how to recover, maybe how to write down hyperkähler structure in this coframe. This coframe. So to this end, we will need one more auxiliary function. So this function will be, I will call it V. It will be the norm of this vector field generating S1 action. So the norm to the power -2, or g of x to the power -1. So it is a smooth function on M0. But actually, since it's invariant with respect to S1 action, we really can think of it as a smooth function on the base space. And one extra piece of data which we'll need is a Euclidean metric on R3. So this will be Euclidean metric with respect to this preferred coframe. And we have this eta, which is connection one form. I just copied here. From this, you can write metric G as follows. So metric G will be V times Euclidean metric plus V inverse times eta squared. Now, what is the relation between connection one form and function V? Well, it happens that they're related to each other through the curvature form. Specifically, the curvature form of this connection happens to be the Hodge dual with respect to Euclidean metric of dV. In particular, this identity implies that V must be a harmonic function with respect to the usual flat metric on R3, or rather with respect to pullback of this metric. And I mean, you can write also explicitly what the complex structures are. Basically, you can write explicitly the action of complex structures I, J, and K on this in this coframe. So it will go something like action of I on 8, that will be dmu1, and it will map dmu2 to dmu3, and then the remaining are recovered with cyclic substitution. But the most important data for us will be the metric. I mean, the rest is more straightforward. So what I have written down here is how you can write explicitly any given hyperkähler metric with S1 action, with a free S1 action locally in this nice coframe. So what happens that this construction is reversible. This description is reversible. So in the following sense, what you can start with, three manifold N0, which is openly mapped into R3. This is your first input. Second input will be a function V, which is a smooth function on N0. Non-negative, so with non-negative values, and solving Laplace equation. So Laplace equation with respect to the same Euclidean metric of V equals 0. I mean, if I want to be overall pedantic, maybe I want to call this map I, and then this will be a pullback of metric of the Euclidean metric. That's really what happens. What's going on here? And so this is one assumption. Another assumption, which is kind of clear here, clear in this picture. You want also to assume that star h of dv. So it's a closed one form because v is harmonic. So this closed one form, you want it to live in the integral second homology, not in the real. So you want to have it integral periods essentially. So with this last assumption, then this class is integral. You can construct S1 bundle with Euler class given by this class of this curvature form. So it will be S1 bundle like this. And the metric which you can now write, so this metric will be V times H plus V inverse times, maybe let me be a bit more careful here, what I want to say exactly. So maybe I split it into steps. So you choose connection with curvature star H dV. So there is actually a choice here. There is no choice if your region, if N0 is simply connected. If it's not simply connected, there is a choice here up to gauge. Choose connection eta with this curvature. Then M0 and metric given by VH plus V inverse eta squared is hyperkähler. I'm not specifying complex structures, but they also can be specified explicitly through this coframe, which is given by this connection one form and pullbacks of coordinate forms on R3. Maybe let me give you an example to show how it works in practice. Example, well, the easiest example in all the examples, N0 will be just an open subset of R3. So the easiest example, which will be that N0 just equals to R3. So you're looking for a positive harmonic function on the entire R3, but any such positive harmonic function on R3 must be constant. So V equals constant. If V is constant, your curvature is 0, and so you have trivial bundles. So your manifold is really R3 cross S1, which is hyperkähler if you think of it as a quotient of the linear quaternionic space by translations. So this is one example which you can consider. So this is sort of not interesting. What would be interesting examples? So to make example interesting, you will have instead the entire R3 consider something proper, some subset which is not all R3. So we will consider R3 minus some point, maybe x0. And so we will have a positive harmonic function in the complement of this point. And a harmonic function which you could take will be multiple of the 1 over norm of x. So norm is computed with respect to Euclidean metric. So this constant, specific constant here is important. So if you choose constant like this, you can verify that this class, this will be an integral class in R3 minus origin. So this has non-trivial second homology. So this condition is non-vacuous to be an integral class. And choice of connection, there is only one up to gauge equivalence. So connection is unique. And in this case, what you will observe that your M, topologically, it will be R4 minus origin. And it will be realized as H minus the origin. And the quotient map here, so the quotient map will go from R4 minus the origin to R3 minus this point x0. This is really Hopf aberration. So this construction through this with this specific potential V, it is called sometimes called monopole.
So Yuri, I got confused. So yes. X0 is the origin of R3 or?
So say again.
X
oh
naught.
Here, yeah, x naught. I mean, you can take the origin here. You can throw the origin here. I just wanted to make it any fixed point.
And then V is x minus x naught, is that?
Yeah, sorry, yeah, you're right. Yeah. Thanks for the reminder. Yeah, V of x. Yes, that's what I meant. More questions? So another example which you can consider, you can still take R3 minus x naught. So you still want to take V of x to be proportional to x minus x naught. But the only thing you can do to satisfy this assumption of having integral curvature form plus being positive is that you still write 4 pi here, and you allow yourself for some positive integer here. So k is positive integer. So this is sometimes called multi-monopole. So in this case, your manifold will be, again, a smooth manifold. It will be R4 minus 0, quotient by an appropriate ZK action, by an appropriate cyclic group ZK. Basically, this is ZK sitting inside S1 of this Hopf vibration. And as hyperkähler structure, it will be still flat like this. And we see here a difference. This guy, it could be nicely completed into a smooth manifold. Maybe I should mention that the metric which you get through this construction will be the flat metric. And here you will also have the quotient of flat metric. So while this can be completed into just H, this cannot be completed because this will have an orbifold singularity at the origin. And the way you can fix the last example is instead of R3 minus 1 point, you can sort of make this one point of multiplicity k into k distinct points. And in this case, your potential will be 1 over 4 pi x minus xi. And well, your manifold, this manifold is not easy. I can't write it like explicitly this way, but what happens here? Maybe let me be a bit more specific. So here you will in the previous example you will have completion h modulo zk, and now what you will have resolution of this completion. There are many resolutions. This will be some specific S1 equivariant resolution governed by the choice of your points x1 through xk. This will be resolution.
So in general, what is wrong with orbifold completions?
I mean, nothing wrong with it. It's just orbifolds, and we're looking for manifolds. But in general, nothing wrong.
But in general, when you want to see the solitons as limits in the flow, can you?
Yeah, well, you will probably need to include the orbifolds as well. That's true. Yeah, and here I just wanted to write that this is resolution of the AK type singularity. So maybe let me mention a theorem of Roger Bilofsky from the 90s. So he proved that every complete simply connected hyperkähler manifold M4GIJK with S1 symmetry, and I will need one extra technical assumption that it has finite topology. It can be substituted just with the assumption that this guy has finite Prollinger characteristic, or equivalently that there are finitely many fixed points for S1. Is a completion of the structure corresponding to this potential. Structure corresponding. So this result, I mean, it's quite technical on many levels. So it's not an easy result. And actually, Bilofsky proved more. So he proved it for any 4K dimensional hyperkähler manifold with a tri-Hamiltonian TK action, with a tri-Hamiltonian action with torus. But quite quickly, everything reduces to this fact. And so this is the main part. Kind of amazingly, this gives you an exhaustive answer of what hyperkähler manifolds, complete hyperkähler manifolds with S1 action are, provided you have finite topology.
Can you weight any summand by some positive number, like K1?
Oh, sorry. Actually, yeah. Thanks for the question. So first, actually, I want to mention that I forgot something. So I forgot that you're also allowed to add a constant here. I should have mentioned it. It's actually important. So this constant is non-negative. So for this theorem of Bilofsky to be valid. So answering your question, you can weight this by positive integers, but if you do this, you will get orbifolds instead of manifolds. So if your goal is to classify complete manifolds, then Bilofsky theorem is, I mean, it certainly also stands, even though he didn't formulate it this way. And yes, you will get the classification of complete hyperkähler orbifolds with S1 action.
So for these orbifolds, you have only isolated singularities, or?
for these orbifolds, yes. I mean, and in general singularities, they will be I, J, and K holomorphic.
Okay,
Single locus. So it has to be zero dimensional. So what I'm going to do next, I kind of would like to go back to generalized scalar world and explain how analog of this Gibbons-Hawking ansatz works there, even without assumption of soliton equations. But you really need to assume the presence of S1 symmetry. Back to generalized scalar world. So yeah, looking at the type, it's almost certain that I will not be able to cover the soliton part of this construction. So Jeff, maybe is it fine if I move this discussion of the solitons to the next seminar? And
yeah, no, that's perfect. Yeah, that's perfect.
So I now explain how to give a similar local picture to the Gibbons-Hawking ansatz in this setting. So what will be our input? So we'll have MGIJ with so for this to make sense, we will assume that its I and J is invertible. So in the terms of our previous discussion, we'll be really working on M minus work on M minus the locus where I equals plus or minus J. So an open dense set of what we had before. And we now assume that you have a vector field which generates S1 symmetry of the entire generalized scalar package of Gij. So then on a cover, M tilde of M, S1 is tri-Hamiltonian. I will explain in a second what it means. So, so we really work on a cover. So we really assume that we already work on an appropriate cover on M.
But how do you know that the S1 action stays S1 on that cover?
Yeah, because it's easy to read off which exactly cover you need to take. So basically the cover corresponds to the quotient of the fundamental group, which is related to the quotient of homology, first homology group. And essentially the reason is because S1 vector field annihilates all three one forms to which you want to find primitives. That's the reason.
But is it a finite cover or is it?
No, not necessarily finite. Might be Z cover.
But this S1 action can become R action. So...
No, yeah, it will not. So there is, so it's a claim. It's possible to choose R action, R cover, such that on the R. Sorry, it is possible to choose such a cover here that the action will be tri-Hamiltonian and it will be still on as S1 action. So, and by being tri-Hamiltonian, I mean that you have these three forms, omega, I, x, I omega, and I, x, j omega. So they are always closed, and we assume that they are exact. So yeah, just not to multiply notations, we assume that they exist already on M, and we will not use notation until that. Well, what does it give us? It gives us essentially a very similar picture. You will still have a map from M minus fixed points. This will be fixed points. Maybe I will call this M0. So you'll have projection onto the orbit space, which we'll call N0, and there will be an open map to R3 through this moment map, which I, by use of notation, still call mu. So this is moment map defined by these three functions. And you still have a nice coframe. You will still have coframe d mu I and the connection one form as this in the same, which is constructed in the same way as before in tangent space to M0, cotangent space to M0. So the question, can we recover all the structure before from a scalar function as we did in hyperkähler case? So the answer to this exact question is no. It's not enough to know one scalar function to recover the entire structure. However, it's worse as in hyperkähler case, but worse by a tiny bit. So it's enough to know two scalar functions. Maybe let me explain what I mean here. So I still want to cook up a metric on R3. And before, if you remember the metric, it was just a flat metric in this mu1, mu2, mu3 coordinates. So this way we'll still have a preferred metric. This metric will not be flat anymore. It will be controlled by one scalar function. So we'll write specifically this in coordinates, and I explain the notation. So what is this mu2? This p. So this p is actually a new thing which appears here. So this p is a so-called angle function. So where p, again, on the nose, it lives on M0R. But really, since it's invariant on the S1 action, we will think of it as a function on N0. So really, this metric also will live not on R3 but on N0 to be precise. At least for now, for this part of construction, it's a metric living here. So this p is the angle function. Which is defined as -1/4 trace ij. So I'm not sure how this is, how this function is, whether this definition is illuminating at all. To me, it was a bit mysterious at first. The way you can think about this sort of geometrically, that these I and J, they are two complex structures inducing the same orientation on a four-dimensional manifold. So they live in one twistor family, and at a given point, the complex structures with prescribed orientation on a four manifold, they could be identified with a two-dimensional sphere. So this is a family of complex structures with prescribed orientations in a four-dimensional space. So what this p measures really is a cosine between I and j. So this cosine of this angle is what we call p. And in particular, I should mention that if this p is constant, that what you really can do, you can choose another representative, maybe j prime in the same family, such that I and j prime, they will be just hyperkähler. So they will be at a constant angle 0 from each other. And in this case, they will be both integrable. They will be just members of a hyperkähler family. So this function, really under our assumption, it takes values from -1 to 1, because remember, we assume that I is not plus or minus j on our set. So we have thrown away this locus where I is plus or minus j. So the values the angle function takes is from -1 to +1 excluded. So maybe maybe I can actually now. Oh, okay, let me first do it as before. So first, let's do given a generalized scalar manifold with symmetry. Let's recover all the structure. So then we still can consider the same function. We can consider g of x inverse. And then the claim is the following: that function v, function p, and the connection 1 form are related as follows, are related to each other. As follows. So curvature form, the differential of connection 1 form. So this is connection 1 form. So it leaves among the 1 and 0 r. So it's curvature. So before it was just Hodge dual of dv. It will be not as simple this time. So it will be Hodge dual with respect to this non-flat metric plus an extra term. But this extra term will not be bad. It will be an explicit 2 form times v. Maybe I should write it down. I mean, it doesn't really matter much for what we're going to discuss, but this beta 0 is fairly explicit. It's so the geometric meaning of this 2 form is still a bit mysterious to me. So why doing it exactly this form and not something else is something I don't really understand. So I believe there should be some intrinsic geometric interpretation of this form, but I don't know what it is. This beta 0. So correspondingly, you also have the certain operator on V. So this operator is just essentially star D of the above thing. So this must be 0. So this is second order linear elliptic equation for V with a given P, with a given P. So if function P is fixed, this will be just a linear elliptic equation for V. It's like Laplace equation. It's just a bit more complicated this way. So whenever you have generalized scalar structure with S1 symmetry, you'll have this structure. So the point is that you can reverse it. So conversely, you can use, you can start with functions V, P, and connection 1 form, satisfying these equations, and you can recover generalized scalar structure on the total space of the principal S1 bundle, as you can in the given Skockian ansatz. So maybe let me make this precise.
So this is completely local. You don't need really S1 actions or any of the global things.
I mean, for this part, if you assume that your action is free, well, yeah, for this part, yeah, you don't need. Yeah, it works for our action as well. Yeah, when I will be discussing solitons, I will need the properness a lot. But again, I imagine that it can be bypassed. It's just, I mean, there are already many technical details building up on the other in the entire construction, and we, Jeff and I, sort of felt that this, when you have our action, which is not proper. It will force you your isometry group to be larger. And we thought that we could treat that simultaneously with that other case where IVI and GVG are not aligned with each other. So that was the reason why we didn't really want to complicate things further technically here. But you're right. So this specific part, it can be, it's all local. It will be the same if you assume that you just have R action. And actually, our action here must be proper. It's actually a feature with this local construction, basically because it will be, because moment map is constant on the orbits of the orbits of vector field X. It's when you go back to the quotient, you will lose this properties. Are there more questions?
What is the metric in this case, in terms of the?
Right. Yeah. Sorry, I should have written it. Yeah. So the metric is exactly as it was before. So actually, I will write it as the statement of the theorem, which I'm about to mention. But it's the same expression as before. So theorem. Let's call it Gibbons, Hawking, ansatz for generalized scalar metrics with S1 symmetry or with one-dimensional symmetry. So you start with three-dimensional manifold, which is openly mapped into R3. And you take smooth functions. So first will be what will become angle function. So its range will be from -1 to +1. And function V with the range from 0 to +infinity. Such that first that this D of star H dV was, or maybe I should write down that you construct metric H. Construct H on N0 as above as we have done here. This metric on N0. To construct this metric, you will need P. And you assume that the following some conditions are satisfied. So star H of dV is V of beta 0 equals 0. So this two form is closed. Now you assume as before that this closed form actually represents an integral class. So it's a closed form, it represents a class in the second cohomology. With the base space, you want this class to be integral. Then you construct S1 bundle with curvature. Maybe I should say with early class because it's basically it's topological part. This early class as above. Then you choose a connection with this curvature. This curvature. So it will be somewhat important for us. Maybe actually not really, but I just want to mention that there is a choice if your N0 is not simply connected. So yeah, it will not be really relevant to us. But I can imagine that in some sort of constructions it might become relevant. So there is a finite dimensional family of choices. So you choose a connection again. I'll call it eta as before. So what else do I need? So as one bundle here, I will call it M0 over N0. Then M0 admits generalized scalar structure with metric G, well, the same as before. It will be V times H plus V inverse times eta squared. And maybe I will also write omega I. So this will be the complex valued 2 form, which is 2-0 form with respect to I. So particularly, it completely determines I. So this form is given by, I'm not sure how important really this exact presentation is, but just to give you a flavor of what type of things appear here. So it's fairly explicit. It's not super illuminating, at least to me, but it can be dealt with, and you can work with it if you want to understand something about the structure. That's exactly how we will be proceeding next. And omega j, again, also fairly explicit. I just don't want to right. Exactly. So Francis, does that answer your question about the metric?
Yes, thank you.
Right, thanks. Are there more questions? So maybe let me give a concrete example. Again, I'm not sure, actually a couple examples. I want to discuss 2 examples and maybe stop for today, and then I will go back to solitons and then explain how really soliton equation enters this picture in the next week.
Yeah, one question, Yuri.
Yeah.
So what happens upstairs if you're in a situation where you have a actually hyperkähler, but you take this p, this angle function to be non-zero? What type of structure does it give you?
So okay, so if p is identically 0, this is exactly the Gibbons-Hawking ansatz, right? If p is constant by non-zero, then it will be still Gibbons-Hawking ansatz after a linear change of coordinates in R3. So linear change of coordinates in R3 will turn whatever you have here into the standard Gibbons-Hawking ansatz. So it's nothing new.
So can you give conditions for orbifold compactifications?
So yes, that's something I'm working right now, and my expectation, not expectation, yes. So it's fairly easy to show. It's essentially the same argument with Gibbons-Hawking, with a bit more, slightly more careful to show that it's still true that you can compactify this as orbifolds if. Okay, maybe I should back off a bit. So actually, yeah, I'll back off a bit, and it's not as easy as I want to say. So in this setting, if you don't assume soliton equation, it's actually something we don't know completely. Specifically, you can imagine that that you can take potential as above, which solves equation like the Laplace equation equals delta function as before, this Green's function, as monopole potential above, and then you will be able to compactify it by gluing in a point and extending structure over this point. Unfortunately, we were not able to prove it here. It sounds like a technical thing, and I still wish we proved it. For Soliton's construction, we didn't need it, and for classification, but overall, for working with generalized scalar structures, it would be definitely useful. So we don't know how and when you can glue back fixed points to M0 to make it complete. Because remember, we removed fixed points to make it principal bundle. What we were able to prove that you can extend all the structure in the C11 sense. So metric in the C11 sense and H in C01 sense. So in some like continuous or weakly smooth sense, the structure extends to fixed points.
So something is not sufficiently elliptic to get a bootstrapping in that case? Is that what's going on?
Yeah, basically you don't have any elliptic equation on your ambient manifold. You have elliptic equation on the base space, but this elliptic equation has this pole at a given point, and you need really good control of how the pole of the structure of the pole. Basically, it is possible to get to do into Gibbons-Cognate ansatz because your pole is SO3 symmetric. Your function, yeah, as basically you have something smooth plus something with a pole which is SO3 symmetric.
So what about extending first the complex structures and then you use a holomorphic type of?
So yeah, that's something I tried. It's first to use this Nylander-Niedermeyer theorem because it applies, and your I and J separately they can be put into holomorphic atlas. Maybe I'm just missing something simple, so I wasn't able to overcome this. It does seem like a simple technical step. I don't know. At some point I thought for a while, and at some point I just gave up because, I mean, what we needed with solid equations, you do have this elliptic regularity which you mentioned. I'm 100% certain that it should be extendable in all cases, and there are more cases than generalized than Gibbons-Cognate ansatz when we have this smooth extension. Somehow we just weren't able to overcome some technical issue here. And yeah, answering your orbifold question, that orbifolds with extra soliton equation, yes, you can prove that they will form the same type of orbifold singularities as Gibbons-Cognate ansatz. But this is something I'm writing up now. We didn't put it into the paper. Okay, so yeah.
In the hyperkähler case, there is this idea coming from physics that if you write down all the holomorphic volume forms in a family depending on the twistor parameter, then this has some very nice properties. And can you do something similar here? Like, is there like a natural twistor parameter and you can write down like a family?
Yeah, I'm not sure. So I mean, maybe the thing with twistor parameter here that you don't have integrable complex structures in your twistor family. You have only two integrable complex structures, I and J, and normally that will be it. You still can deform them into almost complex structures. So maybe you can consider twistor space and work on that. But I don't know exactly generalization of that. It will be interesting to know. One other thing which actually I'm trying to figure out right now, so this Gibbons-Cognate ansatz, it has an alternative description through hyperkähler modifications. So this is something related to hyperkähler reduction. So you can take hyperkähler manifold with S1 action, you can multiply it by the standard H with diagonal action, by the flat space with diagonal action. And so you'll have actually a torus action. And on this product, you can perform hyperkähler reduction. And this will be, in a sense, it will be equivalent to adding a pole to your multi-monopole potential. So it appears to me that something very similar happens here, that you can take Gibbons generalized Kähler structure appearing from this construction, take direct product with hyperkähler structure and perform some sort of hyperkähler reduction. And it will be nice to have such an alternative description, in particular because it might resolve this issue of extending smoothly the structure. Which I mentioned.
I guess this beta 0 form relates to the torsion of the B-formation structure. Is there like a clean formula for that?
To the leaf form, you mean?
No, of the torsion. I mean, if beta 0 is 0, then Or yeah,
Yes.
maybe it's
I mean, you mean torsion as H, or I mean, yeah, which is equivalent to form in 4 dimensions.
Yeah, okay, yeah,
sure. No, they are genuinely different. For the soliton, I can tell. For the soliton, this beta 0 will be just so soliton. Then beta 0 will be just star df, star with respect to H. But in general, yeah, general, I don't know. Again, it has to have some intrinsic meaning, but I don't know what. Well, I think it's right here. That, yeah, it should be right. Okay, so yeah, I'm a bit out of time. Maybe let me do one example. It's the simpler one, and then we'll see if we have more time. So the simplest example, this is the first example you should ask, because this is the simplest example of generalized scalar structure, which is generically invertible with I commutative chain invertible, which is non-Kähler, and this is Fraunhofer. So you can consider C2 minus the origin, so with coordinates say Z1, Z2. So in this way, you will have a canonical complex structure. Let's call it I. And you can cook up a second complex structure by considering involution, as I mentioned. So there is involution, which is preserving gravitation. Which can be thought of as a inversion as in the unit sphere, composed with reflection in, say, Z1 equals 0. Then on this gadget, you will have two complex structures. You will have the standard complex structures on this as in a complex manifold, and you will have J, which is a pullback of I under this involution. And the way I think about it, you have C2 minus the origin. And on one coordinate plane, you'll have I equals J. And on the other coordinate plane, you'll have I equals negative J. And in the middle, they will be of the same orientation and not plus or minus each other. So it means that really here you have C star squared. And this is a locus where I is not plus or minus J. And if you work with this manifold, then if you take any natural S1 action, it will not be Hamiltonian or it will not be even Hamiltonian for just omega. It will not be Hamiltonian, tri-Hamiltonian as well. So you want to take universal cover of this. This is exponential map. And if here you take coordinates like x1 plus y1 and x2 plus square root minus 1 y2, and if you work through what I have discussed, maybe I'll just first write down the symplectic forms. So omega I is the easier one. It's just a standard symplectic form in this logarithmic coordinates. And omega J is the one obtained via this involution. So again, it's fairly explicit. Maybe I'll just write it once. I don't need that much for explicit picture. It kind of shows why all these dialogarithms always appear when you try to do some potentials for Hopf surfaces. Log of the same thing, minus x1 minus square root of minus 1 y1. So they share a common real part, and they have not opposite, they have different imaginary parts. And you can consider the standard diagonal action of S1 here. So if you consider this diagonal action, then what you will have for your moment maps will be argument z1 minus argument z2. U2 will be log of the ratio. And U3 will be a bit more ugly, but again, you can just get it from the involution. Maybe if just to give you sort of intuition of what's going on, this angle function will look like this. So it will be exactly plus or minus 1 on this two coordinate axis, and it will be between plus or minus 1 elsewhere. And again, it's I will not go through this calculation, but it's again fairly straightforward to check that with this moment coordinates you can recover the round metric for the Hopf, and you can also see that these forms they match the same forms here. Maybe what I mentioned that from these formulas, it's sort of evident that you have to take universal cover because this is not a single valued function if you treat it on C star squared. So, and in principle, so this is all written for X, which is a standard diagonal action on C star squared, so which is a real part of Z1 del Z1 plus Z2 del Z2. But you can also consider some multiples here to real numbers, and they don't have to be commensurate to each other. And this exactly then will generate R action, which will not be proper.
So what is V in this example?
Yeah, I didn't write it for myself this time explicitly, so let me try to recall myself. Yeah, well, okay. Okay, yeah, I do have, yeah, I do have.
I'm just curious, it's not important.
Yeah, all right, it's fairly explicit, yeah, it's you can deduce it from what we have written. I just, yeah, I can write it off the top of my head. But yeah, it's explicit through this mu1, mu2, and mu3. So this is something simple which we have seen before. Something less simple, maybe the last construction which I would like to mention. This is Lebrun's construction of GK structure of a Louis surface. Lebrun's GK structure on parabolic Louis surface. So it looks a bit different from what we did. It looks similar still, it's different, but in the end I will show that it matches exactly with the same ansatz as suggested by this theorem. Well, it has to by this theorem. But on the surface, initially it will look a bit different. So the way Lebrun's ansatz works is as follows. So you start with hyperbolic space. So it will be X, Y, Z. Where Z is positive. And you take hyperbolic metric. So it will play a different role than our H. So I denote it as H tilde. So it's a usual hyperbolic metric on this upper half space. And you can still cook up a potential similarly to, say, Gibbons-Hawking ansatz. And again, it will play a different role than our V. So I play V tilde, put V tilde here. So it will be sum of monopoles. Monopoles are still fairly explicit here, but we don't really need them. So the monopoles are functions solving this Laplace equation. Minus 2 pi delta pj. So pj are points in this hyperbolic space, some specific points which I mentioned in a second, and there will be z worth of them. And this Green's function goes to 0 at infinity. And the picture goes as follows. So you have this z equals 0 plane, you have z-axis where x and y equals 0. And these points pj, they are located at points of the form 0, 0, lambda to the j, where lambda is some positive number, the number greater than 1. So you can show that this series is absolutely convergent. So this will be a smooth function solving Laplace equation, where on the right-hand side will be a sum. You will have a sum of this Dirac masses. So then you can cook up a metric G, which again I will write explicitly. It's similar to Gibbon's Cohen ansatz. It's a bit different. So it will be a conformal factor of something looking like Gibbon's Cohen ansatz. Again, with understanding that from this V, I can cook up a 2 form, and this 2 form will be the curvature form of some one of connection of some principal bundle. And this metric is incomplete. It is incomplete. It is incomplete for 2 reasons. Well, first reason why it isn't complete, because we need to remove these points to really make sense of what V tilde is. So to complete it, we'll need to glue them back, and gluing them back on the level of the total space. This is a total space, which is a principal bundle of H minus this collection of Pj. So we need to glue back this point, so which corresponds to gluing fixed points of S1 action here. But it also is incomplete because this part is at finite distance with respect to this metric G. So you also need to glue in back this punctured plane here. So can be completed with, so if I call this projection pi, by abuse notation, I can write it could be completed with pre-images of this removed points, and this will be fixed points. And then you also need to add z equals 0 minus the origin. And then on this manifold, which you obtain by this completion, maybe let me call M, it admits Z action, which is just contractions here. So this whole entire picture is invariant under contractions or scalings. And you can leave these contractions to the principal S1 bundle. And the quotient, this will be free action, and the quotient will be a compact surface. Which, as a complex analytic surface, will have an interesting property. The preimage of this z-axis will be a chain of k curves, and where maybe I should write this contraction takes pj to pj plus k, and it picks some number 2. And there will be a quotient of this green locus by contractions, and this is just an elliptical. So this is how the quotient looks like. So this is something called parabolic inverse surface. And to relate it to our construction, to really see what is our H and what is our V here, we just need to rewrite this expression for the metric a bit. So if you take this expression for the metric, you can write it equivalently as follows. So you can write it as times V tilde multiplied by square H tilde plus V inverse at a square. So this is our new V, and this is our new H. And then this equation, which we implied here. So equation that Laplace V tilde with respect to H tilde equals 0 is equivalent to this equation for function V, which appears in Gibbon's Hawking ansatz, which I mentioned above. It's equivalent, maybe let me scroll down for a second. It's equivalent to this equation. Yeah, I forgot to mention one thing. So from what I discussed only one complex structure on the new surface, but there is a second complex structure which can be obtained through inversion, this time in this hyperbolic space. So this is indeed generalized scalar structure, and it should be we should be able to obtain it through our ansatz, and this is how these two are related to each other. So probably I'll stop here. Thank you all for attention, and hopefully I'll continue next week.
Yeah, thanks, Yuri.
Can I ask, what is the relationship? Like, what is the statement that you made at the end about relating G to the Gibbons-Hawkins construction?
Right. So this construction, which yeah, very briefly sketched here, it gives you a generalized scalar structure on this Inouye surface with S1 symmetry. And we know that it must be obtained at least locally by this ansatz. This is part of the theorem that locally any structure appears like this. So therefore, we should be able to identify function V and metric H in that terms. And they should be related to this function V tilde and this hyperbolic metric H tilde. And the relation is specified here. Does make sense.
So presumably these Inouye surfaces will have much bigger families of generalized scalar structures than just this conformally flat half.
Of course, yeah. I mean, you can deform this. That for sure is true. I mean, there is an explicit family which you can put on here. I mean, there is an explicit family with S1 symmetries. Actually, I don't know. Probably there exists a family which breaks the symmetry, but that's kind of unclear to me. You can, well, you can actually do locally flow construction and break the symmetry, right? So with a flow construction, you will get.
But perhaps the point is that Lebrun really constructs half conformally flat metrics.
Yeah, that was his point. It and he didn't really care that much about Inouye surfaces. He more cared about blown up Hopf surfaces. That's true. Yeah, he had a different kind of starting point.
Maybe just historically, the whole interest in bihermitian from a mathematical point of view was that it was believed that it will help constructing half conformally flat metrics.
I see.
I think that's one basic example, and I think Pontecorvo and Fujiki actually developed this much further using twistor methods. Maybe there are ways to construct them differential geometrically as well.
Mm-hmm. You mean using something like twistor spaces?
Yeah, they do use twistor theory, but it should be also direct type of approach as well. Yeah, so there are many half conformally flat bihermitian examples now.
So by half conformally flat, you mean that on W plus or W minus is
one of them.
Yeah, yeah.
Did you think of what is the formula for the generalized scalar potential in this matrix that you construct?
Well, I mean, from what I understand, generalized scalar potential is sort of a relative thing, right? So it allows you to relate some background choice to a given structure. And yes, I did it actually for Lebrun's ansatz. So I wrote down some version of the generalized potential. And again, it basically depends on which coordinates you choose to write it down. You can do that, but I don't know how to incorporate the degeneracy loci, and it's not covered by the present form the generalized scalar potential is stated, because this is not a symplectic type. You have F plus and F minus both have degeneracy loci. So you can look at the generalized potential on the dense open set, but then there will be these tricky questions about how to extend it. And potential will not be extendable in most cases. So you'll face situations where you cannot extend potential to smooth function, but the structure which it defines is extendable.
So you were mentioning before in the explicit example on the Hopf surface that somehow this explains why the D logarithm appears, and also this D logarithm was appearing in one of the formulas of Marco and
yes,
Francis.
well, because basically you will be needing to integrate expression like this, or this thing divided by e to the, I mean, the difference of certain logarithms. Yeah, I mean, it's really a mathematical statement I wanted to make, but yeah, you will need to integrate something like this difference, and it will give you a D logarithm.
Maybe that's a sign. I don't know. Any other questions? Well, yeah, thanks again, Yuri.
Yeah, all right. Thank you.
I'll stop the